But anyway, as always, back to discrete math. Let's get started. So, last time we were finishing up our conversation about these multiple quantifier situations we have going on. I'll just write down multiple quantifiers. That's what we're dealing with. And we've already talked in depth with the double existential, so we're moving on to the double universal. Because remember, we said if you're gonna have a predicate, if you have predicate P of xy like that, you want to make that into a statement, right? The way you make it into a statement is by claiming this predicate is true when plugging in certain x's and y's, right? And the whole point of quantifiers is to specify on how much of the domain for x you're saying this is true, how much of the domain of y you're saying is true. Because once you've specified that, you actually have a real statement. You're saying P of xy is true on these specific domains or on this certain part of these domains. So that's the whole point. And we said there's 6 ways we can do that. We have this way, the double existential, the double, this is the double universal, right? And then we have these mixed right here. These are going to be really interesting. But let's just do a couple of examples with the double universal first. And this is going to be a ton like the double existential with some twists. So what's a good color? Blue is good. So this is the second one, and this is double universals, and they have the form for all x and d x, so dx is the domain for x, for all y and dy, P of x, y is true. And here's the thing to notice. Just like the existentials, this guy right here, I'm going to call it P little squiggly x, because this is a predicate, right? If you plug in any x to this right here, it becomes a statement. It's a for all statement, right? But it is just a statement. So if you plug x into this, it's a statement, meaning exactly what it means to be a predicate. So this is really just a universal statement for all x in dx. We have P of x. It just so happens that this P of x is a little juicier than normal. It is a universal statement. Alex, hello, welcome.
Hello.
Crew here today. Alex, unmuted for a second, which is the equivalent of going,
Hello. Sorry. Hello.
What?
Hello.
How's it going?
Doing all right. My lab ended earlier than usual, so I get to show up.
So you get to make it. Nice.
Hey.
Well, welcome. Yeah, yay. My lab ended early. Now I get to go to discrete math. So we're talking about double universals. So this is the point about double universals. They're really just a universal statement with the universal statement inside of it. So let's do an example. Example could be every all-star player plays for every team and we had the Lakers, the Nuggets, the Celtics, and the Heat. So this is in context too. We kind of defined these things earlier in the last example. We're kind of piggybacking off that. So every all-star player plays for every team in this set of teams right here. This is equivalent to what? If we're using these definitions right here. For all U in DU, and then, yeah. So every player, what? So for all U and DU, what are we saying happens?
All of the all-star players in the set of all-star players.
Yep. But I'm sorry. The translate the rest of the sentence. So we kind of already have for every all-star player. That's for all U and DU. Then how do we translate the rest of the sentence?
Such that for all, I don't want to use W, in DW.
Oh, it's a V. I'm sorry. Yeah.
Well, I don't like V because my handwriting is awful, but
Okay. It doesn't matter. I'll change it for Alex. For all
okay, thank you.
and hey, that's what you get for personalized class right here. And you know what? I'll say this is equal to DW. There we go. Which, by the way, DV, my initials, Daniel Valvo. Middle name is W. So put them together, DWV. Those are my initials. Any guesses on the middle name?
William.
God, everyone gets it. Yes, it's William. Not exotic at all. Yeah. So for all U and DU, for all W and DW, we're saying R of UV. Because that means U plays on team V. This every all-star player plays for every team. We're saying is for all players, and it's domain of players, and for all teams, domain of teams, that player plays for that team. All right. And I will do a disproof. And so this is not true. Why isn't it true? There's kind of, even if you know nothing about basketball, there's one obvious reason it's true. Or it's false, I'm sorry.
Because you can only play for one team?
Because you only play for one team at a time, right? Yeah, exactly. So disproof, for example, we could use LeBron James again, or we could use, let's use LeBron James. He's famous. We'll go with that. So LeBron James, and Safa likes him. So LeBron James, or I'm sorry. So let's start here. So remember, this right here is and I'll write it again, as this is saying for all X, or for all U in DU, we have what I'll call R squiggly U, and R squiggly U is this right here. So this is really just a for all statement where the predicate happens to be another for all statement wrapped in it. The point is, how you disprove for all statements?
You find a counterexample.
Find a counterexample, right? So we just have to find a counterexample of a player, right, in our domain of players, an all-star player, that doesn't fit this, that doesn't play for all the teams. So let's let U equal LeBron James again. Let U equal LeBron James. Now here's where it gets interesting. Now we want to show that not are squiggly, right? The way you prove a for all statement is you show that there does exist a player that doesn't satisfy the predicate, right? There does exist something in the domain that does not satisfy the predicate. So we want to show that this player, LeBron James, makes this predicate false. But note, RU, once you plug in LeBron James, R LeBron James is a universal statement. Right? So to prove it false, right? To prove this false when you plug in LeBron James, how you prove false a universal statement? Counterexample again, right? So to prove this false, we have to find a counterexample of a W in DW. There you go. Of a W in DW that makes R VW false. So we need counterexample again for this inner for all. So the counterexample, I'll say, is let W equal Celtics. I'll say consider W equal Celtics. Then LeBron James does not play for the Celtics. He plays for the Lakers. Or I'll say LeBron James plays for Lakers, not Celtics. So R of UW is false. Just like we wanted to show, therefore, not every player plays for every team. Or not every player in DU plays for every team in DW. Little square because we're done. Does that make sense? I mean, they should be really simple. The point of this, the reason I'm spending so much time on it, is the point is no matter what really convoluted, complicated statement you have, just kind of start from the left and work your way right. Go, okay, I'm trying to prove that for all U and DU. If it's false, I just find a counterexample. So I got to find a counterexample that makes the predicate false. What's the predicate? Then you zoom in. Then you got to deal with that. And then if there's more statements in there, you zoom in and deal with that. You're just going to keep going like that. Good? Good. Cool. Now, there another way to disprove this, by the way. I'm not going to show it for time reasons, but we used a player that plays on one of these teams. You could also find a player that doesn't play on one of these teams. So, for example, the player Russell Westbrook is an all-star player, but he doesn't play for any of these teams. So, again, that would be false really easy. Like, not only is it, so he doesn't play for any of them, certainly doesn't play for every one of them. Okay.